Hello friends, so today we'll learn all the basic fundamentals of allosteric effect. So these are the contents. So let us first look into what is this allosteric effect, right? So it comes from the word allo, which is a Greek word meaning the other side. And as we know that in an enzyme, there is the active site. The active site is the site which binds the substrate. But in addition to that, in some enzymes, there's also this allosteric site, to which there's a regulator or a modulator that binds. And this allosteric site is called the extra site, right? And this, we have the picture of Dr. Francois Jacob, who was one of the scientists who came up with this phenomena of allosteric effect, right? So let us see actually what happens. So when this modulator binds to this allosteric site, it influences the binding of the substrate to the active site. And this has effects on the overall kinetics of the enzyme and substrate reaction, right? And depending on what kind of binding, we can have homotopic allosteric effect or heterotropic allosteric effect. So what is homotopic allosteric effect? Right, we have written homotropic versus heterotropic. Simply, homotropic is when the substrate is the same as the modulator or the regulator that binds, right? In heterotropic, the substrate is different from the modulator or the regulator that binds. So let us now look into homotropic allosteric effect. We know that in a normal enzyme substrate reaction, we follow the Michaelis-Menten equation, which gives us a hyperbolic curve, which is like the red line. But in allosteric effect, there is a deviation from this Michaelis-Menten equation, and we get a sigmoidal line of which is a S-shaped curve, right? The reason for this sigmoidal line is cooperative interaction. So what is cooperative interaction? We will learn now. So the famous example of hemoglobin and oxygen, right? When we go from the tense state to the relaxed state. So what happens is hemoglobin, as we know, it has 4 subunits which remains in a tense state or in a strained position. But when the oxygen binds, it not only it goes from the tense state to the relaxed state, and the entropy of the system increases. And as we know, the increase in entropy is a thermodynamically favorable process. Therefore, the addition of oxygen to the remaining 3 subunits become even more and more facile. So we see that all the subunits of hemoglobin go from the T state. The 4 were in T state, but as the oxygen adds, it goes on to an all R state. It has to be an all T or an all R state. It cannot be in between, right? This is therefore called an all or none model, right? And because there is a sudden increase of oxygen addition, and then therefore there's a sudden increase in this binding process due to this cooperative interaction. Thus we get to see that S-shaped curve, right? Because in S shape also we see that there's a sudden increase in the binding, right? And now we come to what is activator and inhibitor, right? So what happens is when this in this allosteric site, suppose the modulator is an inhibitor, it binds. So what it does is it changes the conformation of the enzyme in such a way that the enzyme and substrate binding is not favorable or it is not complementary in shape and size. Therefore, the rate of the enzyme and substrate reaction decreases. Therefore, this modulator is called an inhibitor. But when this modulator is an activator, it alters the shape of the enzyme in such a way that is very good complementary shape and size. Interaction between the enzyme and the substrate, and because of this the rate of the system increases, and therefore this modulator over here is called an activator. With this knowledge, now we'll go to the heterotropic allosteric effect, right? And in heterotropic allosteric effect we'll see three cases. The middle line you see is the one, if you remember, is from when there is no modulator. It is a simple enzyme substrate reaction following the enzyme and following the Michaelis-Menten equation. The plus that you see is for the activator. So as I said, and the minus is for the inhibitor. So as we know, for the plus the rate should increase, for the minus the rate should decrease. In all these you see we have plotted the V0, which is the rate versus the concentration of the substrate, right, on the x-axis. And all this we see the Vmax. The Vmax is same for all the three curves, right? It reaches the same place. The maximum rate is same. So what changes over here is the Michaelis-Menten constant, the K value, or what is denoted by the K 0.5, right? We see that for the activator has a lesser Michaelis-Menten value than when there is no modulator or regulator, and the inhibitor has a higher Michaelis-Menten value than when there is no activator or inhibitor. So as you have seen the extrapolation, that the Michaelis-Menten value for the activator is less than when there is no activator or inhibitor, and the inhibitor has the maximum Km value. And this is very much justified because the rate is inversely proportional to the Michaelis-Menten constant. Therefore, we can say the activator has a higher rate than when there is no modulator or regulator, and the inhibitor has a lower rate than when there is a modulator or an inhibitor. And that completes our discussion of all the basics that you needed to know for the allosteric effect. We will come later with some details, but these were the basic fundamentals that you needed to know. So have a good day and God bless.